Now we're going to move into rational functions, and we're going to talk today about the functions, their graphs, their domains, and all of those kind of properties. So we're going to go through kind of 4 key things. We're going to first go through what is a rational function, talk about how to find the domains. Then we're going to look at 2 very specific base rational functions to kind of just get a feel for these things. And then we will talk about how do we find asymptotes, what are asymptotes, what are the different types there are as well. And then we'll kind of combine everything together to get a good graph of these types of functions. So pretty much up to this point, we've been working with quadratics and linear equations. These are really just something known as polynomials. So when you have nice integer powers that are positive, like x squared, x to the 4th, x to the 5th, those represent polynomials. So this is kind of the fancy definition, but basically these numbers out front here, they're just values, real numbers. They're numbers like 5, 6, -3. They can also be decimals like 1/2. Doesn't really matter what those are in front. The key thing for a polynomial is that all of these powers are positive or non-negative integers. So you don't want to have a power like 1.5 or a fraction or anything of that sort. They have to be nice numbers, 5, 6, 7, anything along those lines. So just to give you a couple examples of what a polynomial is, you could see something like f of x equals 3x to the 9th minus 2x squared plus 4. Okay, you don't need every single number in between, just as long as those powers are nice. Something along the lines like 5x to the 8th, that's also a polynomial. Really, even just a constant function 2 is technically a polynomial, okay? And then you can also have, again, decimals as the numbers out front, like you can do 1.5 x to the 10th minus 2. The numbers out front don't matter, it's just the powers, okay? So up to this point, we've really only dealt with second degree, meaning that the highest power is 2. But here the degree is 9, here the degree is 8, here the degree is 10. And here, since there's no x power, the degree is technically considered 0. So when we talk about rational functions, think back to your rational numbers. It's an integer divided by an integer. So a rational function is really going to be a polynomial divided by a polynomial. So when we talk about finding the domains of these, we're now going to have the variable in the denominator. So we have to make sure we exclude values that cause the denominator to equal 0. So let's take a look at some examples of this. We want to find the domain, and we also want to state it in interval notation. So looking at this expression, I don't really care if this simplifies. When I'm finding the domain, I've got to work with exactly what's given to me. So I have my variables in the denominators. I need to find all the values that make the denominator 0. So I need to set this entire expression equal to 0 to find all of our bad values. So remember, we just did this. This means each factor could equal 0. And then the first one's already done for us. We know x equals 0 is a problematic number. For the others, we've got to subtract 2. So this tells us x equals -2 also poses a problem. And then here we add 1 to the other side, and x equals 1 also poses a problem. So the domain for this, just without interval notation, are we need to exclude all of these numbers. X cannot equal 0, -2, or 1. But to actually write this in interval notation, let's go ahead and use a number line. So I've got to put those numbers in order. -2 is the smallest, then 0, then 1. We know we cannot equal these things, so I can't fill in these circles. But everything else is good. So I can equal everything to the left, everything in between, and then everything to the right, just not the numbers themselves. So this domain in interval notation, this first interval is -∞ to -2, can't equal -2. This next interval is -2 to 0, then 0 to 1, and then finally 1 to infinity. Okay. Okay. So this is our domain with all of those problems. Now to kind of give us a little insight into later on, if you look at this expression, there is something you actually can do. So the x plus 2's do technically cancel out, which leaves us with 1 over x and x minus 1. So although the x plus 2 disappears, because of the way the expression is written to us originally, -2 is still a problem. I have to exclude it from the domain. Right? But this will be important again later on when we talk about our vertical asymptotes. All right, let's try another example. So part B, same thing. I look at this expression and I've got to find where this denominator is equal to 0 to find any bad values. So what we need to do is we need to get the x squared by itself, because technically this one doesn't really factor nicely. So this is saying x squared equals -16. And then to get x on its own, we take that square root. But remember, when we take a square root, we get plus or minus. And this leaves us with x equaling plus or minus the square root of -16, which is plus or minus 4i. So really, there's no real number that causes our denominator to equal 0. So because of this, I can really plug in whatever I want, and I'm never going to have an issue. So my domain is going to be all real numbers, from -infinity to +infinity. Okay. All right, so let's look at a graph of two kind of simpler rational functions, and we'll start with these. A lot of our rational functions may have a similar shape to this, but if we can be comfortable with these, then as we start building up, it'll get a little bit easier for the more complicated ones. So our very first rational function we're going to start with is 1 over x. So looking at this thing right away, I know I have a problem. X cannot equal 0. And really for this one, same thing. I cannot plug in 0 for either of these. But that is the only problematic number. So the domain for this rational function is going to be -infinity to 0, and then 0 to infinity. Okay. To get a decent picture of this, I'm just going to go ahead and pick some numbers. So I'll make a little chart. Here's our x value. Here's y. If we plug in x equals 1, y is 1 over 1. So it goes through the point 1, 1. If x is 2, y is a half, so that's right around here. If x is 3, y is a third, which is a little bit lower down here. Okay. Now I'm going to pick some other values. Let's pick 1/2. Your y would be 1 divided by a half. It actually is going to be 2 if you plug that in. And if we plug in 1/3, your y value you're going to see is 3. So we end up with a shape that's going to look like this for these positive x values, right? The only thing that's going to happen when we have negative values is you have 1 divided by a negative number, all the y values are going to be negative as well. So the graph goes through -1, -1, -2, -1/2, -3, -1/3, and then we get kind of the flip shape, and it looks something like this. Okay. So if you notice, for this graph, we hug the x-axis and the y-axis. Okay. So remember, our y-axis has the equation x equals 0, which is exactly that problematic number that we had. It's what caused us to divide by 0. So the value that our denominator cannot equal ends up being this vertical line that we hug. And then we also hug the x-axis, which is the equation y equals 0. Okay? So this is going to be something known as an asymptote in the very near future. All right. The other thing we have to do for this is the range. It's one of the few that we can do that for. So here I can equal every value, but this expression will never actually equal 0. So the range is actually going to be exactly the same thing as the domain. When we move over here and now do 1 over x squared, it's going to be similar, but our x and y values aren't quite the same. We'll start with nice numbers. If we plug in 1, y is 1 over 1 squared. So I still go through the point 1, 1. However, when I plug in 2, this would be 1 over 2 squared. So my y value is going to drop to a fourth. If you plug in 3, it's 1 over 3 squared. It is a ninth. It's even smaller here. Right? If I plug in a half now, this is going to be 1 over 1/4. So this will actually pop up to 4. Okay? And really, I can't do too many other numbers, kind of connecting the dots, though. It has a very similar shape, but it's just a bit steeper. Okay? And now the difference between these two is when I plug in negative values for x, because x is being squared, you're actually going to get exactly the same y values because -1 squared is +1. So you actually end up with exactly the same shape over here, which is roughly like this. Okay? So your domain for this function is exactly the same. 0 is the only problematic number. Our range, however, is slightly different. It's going to be from 0 to infinity. I'm not going to have negative values. Right? And then if you notice, we also hug exactly the same two lines. One of those lines being the value that caused us to divide by 0. Okay. So let's try a couple examples again to get familiarized. We're going to apply our transformation, so it gives us a nice little review on that. We want to explain how the graph of this function can be obtained from either 1 over x or 1 over x squared. Then we want to sketch the graph, and we want to determine the domain and range. So looking at this expression, if we ignore the constants, it's going to look exactly like 1 over x. And then if you remember, this is attached to the x value. So we're going to shift the graph of 1 over x. The -3 tells you to do the opposite direction. So we're going to move it right 3 units. Right? So when I move everything right, we originally had that vertical line that we hugged at 0. It's got to move to the right 3. So it ends up looking something like this. Let's see if I can get this to actually go through 3. There we go. So we're now going to hug this vertical line instead. When I move the horizontal line that we hug, it's not going to do anything at all. And then the overall shape is honestly still the same. You could pick some points to plot it, but we end up hugging these different lines. Okay, so this would be our graph of y equals 1 over x minus 3. When we talk about finding the domain, now because it's been shifted over 3, and right here we know x cannot equal +3, and that is the vertical line that we hug. So our domain is from -infinity to 3, and then 3 to infinity. Because this thing was not shifted upwards, our range is still -infinity to 0, and then 0 to infinity. Let's try one more of these before we get on to the more complicated types of graphs. So here we have the square. So this means we're going to shift the graph of y equals 1 over x squared. And now we technically have two transformations. We have this +2 that's attached to x. So we're going to shift it left 2. And then this -3 tells us to move it down 3. Okay. So our normal lines that we were hugging were the x and y axis. When I move it left 2, it's going to move that vertical line to the left 2. And then this one wouldn't move at all. Now I have to move everything down 3. So we're going to hug down here as well. So we now hug the line x equals -2, which is the problematic value for this function. And then we're also going to hug the line y equals -3. But the overall shape of our graph is not going to change. It still looks like y equals 1 over x squared. And we hug these lines. Okay. And then for our domain, our problematic value is -2, because again, that's that vertical line we hug. This is -infinity to -2, and then -2 to +infinity. And in this case, because we did shift this down, our range starts at -3 and goes to +infinity. Okay. Now that we've got a feel for these basic ones, we're going to kind of bump it up a notch. And we're going to see if I give you any rational function now, and it doesn't necessarily have to be just x in the bottom or x squared, how can we find these vertical lines that this graph is hugging? How can we find the horizontal lines? And how do we find these key components? So we want to talk about finding these, what we call asymptotes. So we have a couple different types. The very first type we're going to talk about is a vertical asymptote. But all we mean by this, an asymptote, is a line that our graph is going to approach. So we have to hug it at some point. For a vertical asymptote, what that means is it's some kind of vertical line that our graph is hugging. So we have a very precise definition that if you're going on to Calc 1, you will see it there. But until we learn a concept called limits, you won't really be able to get a good definition for a vertical asymptote. But what happens is when we try to divide by a very small number, it ends up causing our y value to blow up. So just kind of going back to our graphs that we did of these basic functions, when we pick numbers that were close to 0, both of these fractions get very, very, very large. And they can be very large in a positive direction or very large in a negative direction. So what we say is that our function, it either increases or decreases without bound as we approach that value of x. So you have some vertical line that has the equation x equals some number. So we're calling it a. And when we get close by this number on either side, our y values blow up. It could be that they're doing completely opposite things. So on one side, they're approaching, it's approaching +infinity and the other negative. Or they can both be blowing up to the same thing. And again, what happens after that, don't care about. Just near this vertical line, we're going to hug it and our y values are going to get ridiculously large. So this typically happens when you try to divide by 0, because that's a very, 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 very small number that it makes the y values blow up to infinity. Okay. So just some keynotes. We will never, ever, ever cross through a vertical asymptote. You're going to hug that line. So the way we find these is we're concerned with where does that denominator equal 0, because that's going to be our potential problematic numbers. Well, they are problematic numbers, but it's our potential vertical asymptotes. The one thing you have to do, and think back to that very first case that we dealt with when we were finding the domain, that factor of x plus 2 could cancel out. So we got to scroll way back here, went too far. So in a simplified expression, x plus 2 didn't pose an issue, so -2 wasn't a problem in the simplified expression. So in the case of this happening, there would be no vertical asymptote at x equals -2. Instead, it's what we call a hole in the graph. Okay? So there's a hole in the graph if the factors that are in the denominator end up completely canceling with the factors of the numerator. So when you find the domain, you have to work with the expression that's given to you. When you go to find the vertical asymptotes, you want to use the simplified expression. So let's try a couple examples. We want to find the vertical asymptotes of both of these functions. So in our first one, if I look, it's already completely factored for me. there are nothing that's in common to the top and the bottom. So there are no factors in common to the two. So if I look at this, I want to go ahead and I want to just set this denominator equal to 0. So our vertical asymptotes are going to occur where x plus 2 equals 0 and where 2x minus 1 equals 0. First one's easier to solve. We just have to subtract 2. So one of our problematic numbers is negative 2. So when I think about the domain, our x cannot equal negative 2. And this is also the equation of one of our vertical asymptotes. For the second one, we go ahead and add 1 to both sides to give us 2x equals 1. And then we have to divide both things by 2. So we get x equals a half. So again, this is excluded from our domain, and it is one of our vertical asymptotes as well. So we typically use VA to abbreviate this just because it would be a lot to write. But our vertical asymptotes are going to be the equations x equals negative 2 and x equals 1/2. Remember, these are lines that the graph of the function will hug. So they should be x equals something or y equals something. Okay. For this next one, if I go ahead and I find the domain first, so right off the get-go, I know there are going to be 2 problematic numbers. So one is a little bit easier to pick out. Negative 3 poses an issue from this factor. And then for the second one, if you let 4x plus 1 equals 0, we're kind of double dipping our work. This is 4x equals negative 1 when we subtract it over to give us negative 1/4. That is our other problematic number. So our domain excludes both of these. Okay. That being said, when I go to actually find my vertical asymptotes, we have x plus 3 in the top and in the bottom. You have 2 up top and 1 in the bottom. So this actually simplifies really nicely to x plus 3 divided by 4x plus 1. Okay. So I only have actually one vertical asymptote. The only problematic number that stayed is negative 1/4. Instead, we have a hole at x equals negative 3 because it's excluded from the domain, but it's no longer a problematic number. Okay. All right, so let's talk about now horizontal asymptotes. So these are horizontal lines that the graph ends up hugging. What you can really think of this is the long-term behavior of the function. So again, the definition's a little bit hard to do without the concept of limits. But basically, as your x gets larger and larger and larger, your y is going to approach a constant. It was the exact flip for vertical asymptotes. So for a vertical asymptote, as x got close to a number, your y blew up. So here, what ends up happening is we're letting our x get larger and larger and larger and larger. And we're seeing, does our function hug this line? So maybe here's our first and second horizontal asymptotes. Okay. So as x gets bigger and bigger and bigger, your y value is going to get closer and closer and closer to this line. And it only has to be from one of these values. So on this half, it's where we get very close to the line, so we're good. Okay. Unlike our vertical asymptotes, which you can't cross, you can cross it for a horizontal asymptote. So it could be that maybe I hug on this side and I hug down here, and my graph is nice, we can draw through it. This is also a horizontal asymptote. So because it's a long-term behavior, the stuff that happens in the middle doesn't really matter to us, so it can cross over. When we talk about finding horizontal asymptotes, we're really going to compare the degrees of the numerator and denominator. So I know this is going to look really messy at first, and it'll make a lot more sense once we do some examples. But you're going to look at the highest power you see in the top and the highest power you see in the bottom. Okay? You're going to compare the size of these powers. So in our very first case, if the top is smaller than the bottom, then y equals 0 is going to be our horizontal asymptote. In the case that they are exactly the same power, what we do is we just look at the numbers that are attached to them. And that's going to be our horizontal asymptote. And then in the final case, if the top is bigger than the bottom, then there's going to be no horizontal asymptote. So again, let's just jump into examples, and we're going to find all of our vertical and all of our horizontal asymptotes. So we're getting lots and lots and lots of practice with these things. So we'll always start, let's do our vertical asymptote for this first one. I definitely can't factor 2 minus x cubed nicely, so I can't simplify anything. For the vertical, we go ahead and set the denominator equal to 0. And then going through and solving this, we add 7 to both sides. That gives us 2x equals 7. And then we divide both sides by 2. And we get one vertical asymptote of x equals 7/2. So again, it's an asymptote. It is an equation. Now when we go to find the horizontal asymptote, we want to compare the degrees of the top and bottom. So when I look at the top expression, the highest power I see is 3. So the degree of the numerator is 3. And then when we look at the bottom, the highest power we have is x. So the degree of the denominator is really 1. So this is the case that the numerator is bigger than the denominator. And when that happens, there is no horizontal asymptote. All right. For the second one, we have x squared plus 4 over this expression. I definitely want to factor this to make my life a lot easier. Unfortunately, the top does not factor because it's plus 4. Thankfully, the bottom does factor nicely. So to get 2x squared, we need a 2x and an x. And then to get plus 1, we really don't have an option to do that. We have plus 1 and plus 1. Okay. So to find our vertical asymptotes, we go ahead and set the denominator equal to 0. So that's 2x plus 1 equals 0, or x plus 1 is 0. For this first one, we go ahead and subtract 1 from both sides, and that gives us 2x equals -1. And then we go ahead and divide by 2. And one vertical asymptote is the equation x equals -1/2. Second one's much nicer. We just need to subtract the 1. So our second vertical asymptote is x equals -1. Now to do the horizontal, again, we have to compare the degrees. So the degree in the top is 2, the degree in the bottom is 2. These have the same degree. So because that's the case, what we do is we look at the constants that are attached to them. And technically, because there's nothing attached to the x squared in the top, you really have a 1 there. So all we do is we pick off those numbers. The number attached in the top is 1, the number attached in the bottom is 1/2, and this is a horizontal line, so it's the equation y equals 1/2. Okay, so much simpler than the actual formula states, but again, in practice, much better. So let's try one more of these. We've got x plus 2 over x squared plus 9, or minus 9. Again, want to factor these as much as possible, and because it's minus 9 in the bottom, this does actually factor. 2x and x minus 3 plus 3. So for our vertical asymptotes, we set each of these factors in the bottom equal to 0. And then we go ahead and add 3 for the first one. And do both simultaneously. Subtract 3 for the second. 3 and negative 3 are the two problematic numbers, and they are both asymptotes. Okay. For our horizontal, we want to compare the degrees. In the top, we have 1. In the bottom, we have 2. So this is the case where the numerator is smaller than the denominator. So because that happens, we are going to hug y equals 0, just like we did with 1 over x and 1 over x squared. The top is smaller than the bottom, so we hugged y equals 0. All right. So we can go ahead and talk about graphing rational functions now. Honestly, we're not going to do anything different. We find the domain, we find your asymptotes, we'll find the intercepts, just so we have some extra points. But then you probably need more points too to help get a decent picture, so you have to plot some. So the very first thing you want to do for any rational function is you want to find the domain. Okay. And thankfully this one is factored for us, so it makes life a little bit easier. We have x minus 2 and x plus 2 in the bottom. So this tells us we have two issues where x minus 2 equals 0 and x plus 2 equals 0. So that's where x equals 2 and x equals negative 2. So our domain is x cannot equal these numbers, which then we can write in interval notation. It's negative infinity to negative 2, negative 2 to positive 2, and then finally 2 to infinity. And again, you can draw a number line if you need to put that in interval notation. Second thing we should do is we should find our intercepts. So let's find the x-intercept and the y-intercept. So think about what it means to be an x-intercept. It's where we're hitting the x-axis. So if we're on the x-axis, this means your y value is equal to 0. And then if we're dealing with the y-intercept, if we're hitting the y-axis, then x is equal to 0. So you're really setting the opposite variable equal to 0. The y-intercept is always much nicer because you just plug in 0. That would be 0 minus 1 over 0 squared minus 4. So this is negative 1 over negative 4, which leads us to positive 1/4. So our y-intercept is roughly around right here. Okay. For the x-intercept, we need 0 to equal this fraction. Okay. But the only way that can happen is if the numerator is 0. The other thing you can do is you can multiply this by x squared minus 4, because 0 times x squared minus 4 is still 0, and then you get x minus 1. So x equals 1 is our x-intercept. Okay. All right. Now that we have that, let's also find our asymptotes. So for our vertical asymptote, this thing doesn't simplify at all. We have two problematic numbers, 2 and negative 2. So our vertical asymptotes are exactly that, x equals 2 and x equals negative 2. So let's go ahead and use dotted lines for these. Here's one vertical asymptote. Here is our second. So this is x equals 2 and x equals negative 2. And then for the horizontal, we compare the degrees. The degree in the top is 1, degree in the bottom is 2. So our numerator is smaller than the denominator. So that means we're going to hug the line y equals 0, which is just our x-axis. Okay. So I have some pieces of information, but I still don't really have enough to graph this. I know I need to hug all of these different lines. So the very last thing we need to do is we need to find any extra points that will help us plot this. So let's go ahead and let's make a bunch of extra room. Let's get rid of all of this stuff because we no longer need that now for graphing. Okay. But our fourth and final step is we find some additional points to get a good picture. Okay. So we'll see some x values and see what does y need to equal. And again, we're using this function to figure that out. All right. For the first part, we know we have to connect the dots, so I definitely need to connect these. And I can pick some extra points, but it's got to be nice and smooth, and I've got to hug this line, so it's very likely that it comes downward. Again, you could pick something between 1 and 2 to get a better picture. And then I know I can't come back down to hug the line this way because that would mean I'd have another x-intercept, and I don't. So really what's going to happen is I've hugged this other vertical asymptote this way. But what I can do to really verify that is let's pick the value x equals -1. If we plug that into our expression, this would be -1 minus 1 over -1 squared minus 4. So this ends up simplifying to -2 over -3, which is just 2/3. Okay. So our y value is 2/3, which is roughly around here. So we indeed come up and hug the vertical asymptote this way. So I have everything in between my two asymptotes, but I have no idea what happens over here, and I have no idea what happens over here. We really don't have a ton of options though. So on this side, either I'm going to hug my two asymptotes like this, or I'm going to hug my two asymptotes like this. So as long as I pick just one point, it's going to tell me the case that I'm in. So let's pick x equals 3 and see what does y equal there. So our y value would be 3 minus 1 over 3 squared, which is 9, minus 4. This leaves us with positive 2 over 5. So when x is 3, our y is 2/5, which means we're up here. So that means we're going to have to hug our two asymptotes like this. And then same thing on this half of the graph. I really just need a single number to figure out what's going on because we're either going to hug up here or we're going to hug down here. So we can pick -3 to figure out what's going on. That gives us -3 minus 1. In the bottom, -3 squared is positive 9 minus 4. So this gives us -4/5. So our y value is down here, which now immediately tells us we are going to hug the asymptotes in this way. And this is our graph of the function f. Okay. Let's try one more. We've got x plus 2 over x minus 1. So starting off again, let's find that domain. And thankfully, this one's much simpler. From here, 1 poses an issue. So our domain is x cannot equal 1, which in interval notation would be -infinity to 1, and then 1 to infinity. Now let's find our x-intercept. So this means we set y equal to 0, and then we have to find x. So we go ahead and multiply the x plus 1 to the other side, but it's still 0. So we get really 0 equals x plus 2. And then subtracting the 2 to the other side, we find out our x-intercept is going to be at -2. So plotting in that point, we go through right here. For our y-intercept, we now plug in 0 for x. So that's 0 plus 2 over 0 minus 1, which is 2 over -1, which is -2. So our y-intercept is down here. Okay. Now let's find our vertical asymptotes. And really, I just have one because I have one factor in the bottom. This is going to occur at 1. So our vertical asymptote is the line x equals 1. So we are going to have to hug this line. Okay. Then for our horizontal asymptote, we compare the degrees, and in this case, they are the same degree. So we look at the coefficients attached to them, but there's nothing that's attached to them, so it's really 1 over 1. So the horizontal asymptote is y equals 1 over 1, which is just y equals 1. So that would be this line here. Okay. So connecting our dots, I've got to hug all of my lines, and I've got to go through these 2 points, so I know that my graph is down here. But I have no idea what happens on this side, so we do need some extra points to figure that out. Really, I only need 1, so I can plug in 2 for x. If we do that, our y value is 2 plus 2 over 2 minus 1, which is 4 over 1. So the y value is 4. So when x is 2, y is equal to 4, which is right up here. And so immediately that tells me we are going to hug our graph like this. Okay. So now that we know the graphing, we're going to move into solving equations and inequalities involving rational functions.